I wanted to convert this diol to an aldehyde by acid hydrolysis. So these hydroxy groups will get protonated, but the secondary one is most preferred because it will give a much stable carbocation compared to the primary hydroxy group. So protonation followed by loss of water will form this carbocation, and then internal abstraction of a proton will shift electrons to neutralize the positive charge and shift the positive charge onto the oxygen, leading to a formation of this positive charge intermediate with a positive charge on the oxygen, and then water will act as a base to grab one of the protons, and then electrons will shift to neutralize the positive charge on the oxygen, and then we will form an enol. So we can just stop right here because this is an enol. It will just tautomerize to give the aldehyde that we're looking for, but I just went a step further to explain mechanistically how this can lead to formation of the aldehyde. So electron shift from the oxygen will lead to an attack, or it will cause the double bond to grab a proton from the acid to form water eventually, and then this will form a positive charge intermediate where the oxygen is bearing the positive charge, and so the water will grab a proton from here, and the electrons will shift to neutralize the positive charge on the oxygen to form the aldehyde, and then the acid will reform eventually. So that's how the aldehyde is going to be formed. Yeah. Or you can just stop right here and then just draw an equilibrium arrow showing the shift between this and then the aldehyde. You usually see this in textbooks. Okay, now over here we have this diol symmetrical. This can be protonated, 8 of them. So protonation followed by loss of water. We're going to get this carbocation, and then internal abstraction of a proton will lead to formation of this positively charged enol with a positive charge on the oxygen, and then water will eventually grab one of the protons to neutralize the positive charge, and then forming an enol. Okay, this is an acid right here, so electrons will shift so that the double bond of the will grab a proton from the acid and form positive charge intermediate, positive charge coming on the oxygen, and then water will grab a proton, electrons will shift to neutralize the positive charge on the oxygen, and then we will form the ketone right here. So that's all. Hi, today we are going to talk about conversion of diol to ketones. That is a special case where we are not getting the expected product, but that's how it goes. This 4-membered ring diol is being protonated, loss of water to form this cation. Fortunately, we expected this group to migrate to neutralize the positive charge, but instead the bond right here breaks and then converts this into this. This is neutralized by movement of electrons from the oxygen to form our compound that looks like this 3-membered ring, and this expected is not formed. Why? Because probably this 4-membered ring strained with sp2 hybridized carbon here is just too uncomfortable, so this is formed instead, where the carbons can take care of this 45-degree angle, and that's why this is formed.